Hello, everyone. My name is Susan Charest, and I work for the NTC. And thank you for joining us on our TechCoach event, which does happen monthly. It's a free event really to join people in community and also to do some career development in tech. So I'm going to just frame up today a couple of rules. Just if you could keep yourself on mute to the end of the presentation, that would be amazing. We're going to ask for our host to present for about 30 minutes. And then after that, we will open up the mics for questions. And then you can always drop your question down the chat box if you're a little shy about turning on your mic. So I am really excited about this topic today, effective approaches to problem solving. Problem solving was a critical part of my journey and as in tech career. I'm sorry, all these people are trying to come in. Hang on one second. Hang on. The older I get, the less I can multitask. I'm just saying. All right, let's see here. All right. Okay, so this topic today is near and dear to my heart. One of the reasons why I got into tech 30 years ago was I loved problem solving, loved it. So today we're going to talk about some effective approaches. And so without further ado, I'm going to turn it over to Alicia Novin, who is the Director of Engineering at Celero Commerce. And thank you, Alicia, for being with us today.
Sure. Thank you. And I'm just going to say right off the bat that I'm probably going to go over 30 minutes. So I apologize in advance, but hopefully people can hang out a little longer because it gets better and better. At least that's the plan, at least. So I'll just start off. If you don't know me, thanks for joining. And I'll say that I have about nearing 2 decades in tech. I did my double major in physics and philosophy. So took a different path once I graduated. And I was the kid in my physics courses who annoyed every professor with the philosophical questions that physics professors just don't want to answer. And so that's what caused me to pursue the physics degree, or excuse me, the philosophy degree. But I think with both cases, both physics and philosophy, I am, a problem solver at heart. And I think we're getting a little bit of noise in the background. I whether it's, physics or philosophy or tech or, processes or puzzles or people, I love just solving problems and being the one to solve the problem. But the thing that I've realized over the years is it's become more nuanced to where it's not necessarily solving the problems that I'm gratified by. I mean, it's always nice to have that win, but my passion is really with understanding the mechanics underneath the solution. Like, how did that solution come to be and where did it come from? And that's always what kind of makes me really most excited. So I'll start with this, which is something that is a little bit of a brain teaser riddle kind of thing that I've thrown out for years, whether it's in interviews or with talks that I do at schools or in code camps and that kind of thing. And when I do it in an interview, I never want to make a candidate, squirm and feel uncomfortable. So I always tell them that there's really no right answer to this, which there isn't. It's really just more for me to get some insight into how someone approaches a problem that they couldn't have otherwise prepared for. So I've given it to, young students as early as first grade, I think, straight through to middle schoolers and high schoolers and then professionals. And the reason, well, let me just first give what the actual question is. And I usually paint a much fuller picture, but given that I want to try to be quick here. So the short version of this is that I say, let's imagine that you work for me and you love the company, you love everything that you do. It's a great opportunity and you get along great with me. I'm an otherwise great boss, but I have this one weird peculiarity, which is that every day I ask that you make me some toast. It's kind of a weird thing, but you're okay with it because you love the job so much. So one day you go and you put some bread in the toaster and you push it down and it's not toasting. So my question is, what's the thing that you do next? Now, I don't want us to necessarily solve this on this talk, but what I wanted to share is what I've observed over the years. And this is not like a scientific or research kind of thing that I've done. It's more just what I've noticed anecdotally, which is that the younger that you are, the faster you get on the right approach. Again, there's no right answer, but I found that younger kids are much better at thinking about this problem than adults are. And I think the reason why they are is because if you're a kid, you hear the problem about the toaster and you don't know a ton about electricity. You don't know much about toasters even, and you definitely have no context for workplace life and relationships with a boss and how to maintain any of that. The older you are, the aspects about everything other than to do with the toaster start to distract you, right? The pressures of that workplace and trying to impress your boss and have a good relationship, getting them what they want. And I think that's a pretty important pitfall that we want to avoid, because as adults, that means that we tend to have a bias for solutions of a certain type. Those are solutions that, you know, they either make us look good or they're easier for us to communicate to others. They're ones that we can sell people on. They avoid friction. And, you know, at its root for me, I think that maybe if you find a way to get your boss some toast, that's great. But if you've ignored the actual toaster, you're ignoring part of the problem, right? And so for me, that's more about problem avoidance and not problem solving. So for a long while ago, I was actually trying to see if anyone had ever come up with like an algorithm for problem solving. And I have Googled this a fair number of times. I've read a number of articles and books on it. I've watched different TED Talks and lectures on the whole idea of problem solving. And what I noticed is that, as you can see on the bottom, there's tons and tons of sources that give this kind of process. And usually they use different terms, but it's basically this kind of set of steps where you understand the problem, then you analyze it, and then you're planning your solution, you execute it, and then you refine it. So usually if we were in person, I'd ask, you know, for a show of hands on whether people are satisfied with this. But if you want to either chat, or I don't know if you can raise your hand on the Zoom meeting, but if people are good with this, then my talk is done and I've kind of finished in record time. I'll share that I'm not good with this. And I think, you know, I was just talking about problem avoidance, and I think that this actually avoids the most critical part, which is how did you come up with the actual solution? Like where did that solution come from? Because it kind of just seems to materialize out of nowhere. We just talked about analyzing the problem, and now we're planning a solution. So that's why I'm here, and that's why I wanted to do this talk, because I want to break down the mechanics of how we go from actually analyzing to having a solution, and focus on how those solutions are generated. So with all that in mind, I'm going to start with my thesis now, which is that everyone here knows how to problem solve. I think that everyone here has encountered problems their whole lives. They've gotten to where they are purely because of your ability to solve problems. I mean, we see them every single day. But really what I want to do here is just to shine a light on what you've been doing all along. I want to take what you're naturally doing and doing by instinct, and really just give concepts and tools. And some of them might be new and some of them might be obvious, but I think together, you know, as you build out this framework, it actually just helps you get to the solution a lot faster and avoid certain pitfalls. So, okay. So there's these 3 stages of acquiring a skill that I'll quickly touch on. The first one is this familiarization stage, or it's called the cognitive stage, and that's your shortest stage. So if you imagine like ice skating and you've never gone ice skating, that's where you're picking up the skates and you're getting a feel for it. You put them on your feet and get adjusted to the weight of those skates on your feet, and you get yourself on the ice and you're basically just trying not to fall. So that's your shortest stage, and you quickly move into the refinement stage, or the associative stage. And that's where you start to get better at ice skating. You make fewer mistakes, and you're just doing these minor adjustments, right? Like you might bend your knees more, you might lean forward and just adjust your center of gravity. And then you get to the muscle memory, or the autonomous stage. And that's where things become habitual, they're fluid, and you're not actively having to think about what you're doing. It's just sort of happening. And so what's about to follow is really just a set of frameworks and tools that will not only help you create solutions, but also critically evaluate them. And that's basically how I want to take us from the refinement stage where we're at to getting to this muscle memory stage. So I'm going to start with a different problem than the toaster. This is one that has it was an actual problem that occurred. It has an actual solution. It didn't happen to me, but I think it's a great Reddit and a great example. So the idea is that this IT guy shows up to work one day on a college campus and he gets this email from a professor. And the email basically says, hey, my emails are not going further than 500 miles. So I'm not going to solve this one either. Instead, when I'm going through these tools, I'm going to reference back to this problem and just sort of think of it in the back of your mind about how that technique can be applied to this kind of problem. But I wanted to start with this to sort of capture and highlight one of the most beautiful things about these kinds of problems. And it's what I hate about problems, but it's also what I love about them. And it's just that the problem that we see, the one that we encounter, it's usually not the actual problem that we need to solve. So it could be a symptom or a side effect. Could be far downstream from the issue. So I'll start with the first one, which is low-hanging fruit, which that expression has a few different meanings. I want to focus on just the idea of doing the easiest first. So, if you think about picking apples off an apple tree, the easiest thing to do is just reach out and grab it from the lower hanging branches rather than getting a ladder and getting a long pole and just complicating the issue, right? If you can grab enough apples from the lower hanging branches, you basically solve the problem. So, just think back to that first problem of the toaster. And, one question I immediately ask is, was that toaster plugged in? And kids usually get there very, very quickly. And as obvious as this technique is, how often you found yourself, I found myself overcomplicating it for a number of different reasons, whether it's my own hubris or just the fact that, I've got this thought that it couldn't have come to me unless it was more serious, right? Someone would have checked this already. But if you've ever done something like CPR training, for example, they explicitly tell you as part of that training that during an emergency, you never just yell out, someone call an ambulance, right? They tell you to point to someone that preferably that and you say to them, hey, John, go call an ambulance and come back to me when you're done. Let me know what happened. Let me know that you got hold of them. Because, it's not just about building accountability or assigning it to one person. You're also avoiding that assumption that someone's done and taken care of the obvious thing to do, right? So that way you've done that, or you've taken care of that low-hanging fruit. And pilots do this too. So when they're going through their pre-flight checks, they're not just looking at all the dials and gauges and doodads, they're physically touching them one at a time. Looking at them is never enough. So when they're touching them all and running their hands across them, they're building that muscle memory, or they're relying on their muscle memory at this point, and they're less likely to skip something. I'll give a more extreme example, which is that hospitals were having these crazy numbers of complications after surgeries, just way too high in terms of deaths and post-surgery complications. And all they did to fix it was they introduced a really, what I'll quote, was an absurdly simple pre-surgical checklist. And when they did, deaths went down by 40%, complications down by 30%. And this is important because this wasn't done like 75 years ago or 25 years ago. It was done in 2005. And these weren't small rural hospitals that, for whatever reasons might not know better. These were in major US cities, major hospitals. And this checklist, to give you an idea of how simple it was, has things like wash your hands. So it's things that are easy to forget. And once you put that physical checklist in front of someone, they're forced to check it off and they're forced to do it. So they don't miss those obvious things. So as obvious as this is, I'm going to spend just a bit longer on it because, oh, we're getting a, I'm just spending a little bit longer on it because I think it's really, really important because, if you follow or know the 80-20 rule of Pareto principle, you'll know that 80% of consequences come from 20% of the causes. So what that means is just only a few factors are the cause of our problems, most of our problems. So again, if there's one thing that I want you to take away from this presentation, it's one thing alone, let it be this, because covering those basics first ends up solving a ton of problems and saves you a ton of time and a ton of embarrassment from what would happen if you did all the hard stuff first and then only later came to it. So the next one is to simplify and iterate. And that's all about making the problem easier, starting at the beginning. But honestly, I think simplifying, that's a bit too vague of a term, so I'm going to dissect that a little bit more. So the first one is simplifying by subtraction. And so if you ever heard of this idea of looking for the signal in the noise, you want to remove as much noise as possible and really focus on what you're seeing. And so if you're an agile shop or follow lean principles, you'll know that you want to reduce the work in progress. You want to reduce the backlogs down to what's manageable, because when you have too much, it just sort of compounds and makes things more difficult. And this whole process works well with management or any kind of business process or problem, but it's also really helpful in technical problems, like take computer vision or video games where you're doing some kind of collision detection. So imagine like you're writing a software for a robot that has to navigate its way through 3D space, and you've got all these people that are made up of millions of points that you have to track as they move through space. And when you're doing all of that work simultaneously, it becomes really, really challenging and computationally very difficult. But if you take those people and you just sort of bound them by these boxes and only have to worry about the 4 coordinates of each corner, you simplify the problem dramatically. And not only that, while you've lost a lot of precision about the shape of the object, you've actually kind of built a little bit of a margin that way, because you don't always need to have that precision. So that's what I mean by simplifying with subtraction. And then counterintuitively, you can simplify by addition. And that's where your problem is usually based on something that is a need that is not yet clear. So you just basically want to ask, what is the thing that if I could add to this problem, it would make it easier? And so there's these riddles and computer science kind of puzzles that get thrown out, like this 3 light bulb problem or 100 prisoners problem. The light bulb problem is, you have these 3 switches and you have to somehow know which switch corresponds to which light bulb. And the fact that there's 3 makes it hard because the light bulb is binary on or off. And so it makes it seemingly impossible until you figure out what it is that you need to just add to that problem. Once you've added it, once you introduce that component, the problem goes from seemingly impossible to incredibly easy. So asking yourself, what can I introduce is part of the key. And that sometimes, in different problems, it can be a step in a process, or it could be a role that's missing from your team, or a person, it could be a missing piece of communication, or, like I was saying before, a missing checklist. And then you get to simplifying by isolating. So if you think back to like early algebra, when you first encountered letters getting introduced to math, which for me was really weird because math is supposed to be just numbers, but all of a sudden we're dealing with X's and Y's. If you had teachers like mine, you've heard them say over and over again, right? Isolate X, isolate for X. And you want to separate things and work with them independently one at a time, so you don't actually have them interacting with each other and creating more problems. So, conflict resolution is a pretty obvious example, especially if it's a physical conflict. But, think about like if you're troubleshooting that email that can only go 500 miles, and what could you isolate and analyze one at a time? It's also helpful if you've got a backlog that keeps growing and you want to know what's the thing that I need to isolate here. Or, if you have an outage, for example, those are times where you probably don't want to take this approach because you don't have the luxury of time to be very slow and iterative and deliberate. So you typically then have this knee-jerk reaction to throw the whole kitchen sink at the problem. And sometimes you need to, and that's okay. You do run the risk of not being able to find that root cause that is causing that outage, but you've solved the problem. So the key there is, even if you can just mentally separate the individual variables in your head as you're just throwing everything at it, then it'll help you to maybe just work backwards once you've resolved the problem and see where the issue was. And then lastly, they're simplifying by scope. So, I like this idea of thinking forward, where I don't do it enough, but I've seen plenty of people do it, where they walk into a meeting and the first thing they ask before anyone starts is, when we walk away from this meeting at the end, what is the one problem that we need to have solved? Or they'll ask it differently, like they'll say, a year from now, when we reflect back on this year, where are we? What have we achieved? So from that idea, you get this idea of the MVP, or the minimum viable product, which is a great way to satisfy the bare minimum of any problem space. That could be a product, or it could be a process, a conflict, a technical issue. It could be just about anything related to your code even. Once you've defined what that MVP is, then the next step is you've got to figure out what that critical path is that's actually solving the problem, because even with an MVP, there's a lot of other important components that don't directly relate back to that problem. So starting with that critical path so you don't delay the testing. So that's what I mean by simplified. But step 3 talks about iterating and generalizing. I want to talk a bit more about that too. So as obvious as it might seem, I don't think the depths of that are and how profound it can get are immediately obvious. So I'll tell a quick story about an exercise that I've done with middle schoolers where I've had them come up to a whiteboard, and I'll say, let's pretend that you're standing in the middle of the field and you have this football, and you're throwing the football, and I want you to draw for me the arc of that football as it falls back down. So they draw a nice little curve. And I say, okay, let's now pretend that you pump some iron and you're a little stronger now, so you can throw it harder. Let's see what that arc looks like. And so over top of that original arc, they throw a longer one. And then I say, you've had a healthy breakfast, you've had your grapefruit that morning, so you can throw it even harder. What does that look like? And it gets even further out. And I just iterate with them over and over and over to eventually where they're going off the whiteboard. So I draw planet Earth with a little mountain on top, and I say, okay, I'm going to put you on top of this mountain, and I want you to imagine throwing that ball now. Show me the arc that it takes. And just like this diagram on the slide here, you start to see these little arcs form like D and then E and then F. And just naturally, without having anything to work from, as they have their arcs starting to curve back to Earth, they get to a point where the curvature of Earth curves away from the ball, and they naturally form a football that's orbiting planet Earth. And so this is really profound because, at no point did I talk about gravity or show any kind of physical formulas or talk about forces and gravitational forces. And yet you have this middle school student who, without any of that, they've just shown that the laws of gravity that govern gravitational orbits in space are no different than the laws of gravity on Earth, which was a huge revelation that Isaac Newton had way back in his day. And this was a middle schooler who did it in 5 minutes, just following the right approach. This whole approach worked really well. And, Isaac Newton, Einstein, they were really famous for thought experiments. But I'll quickly also tell a story about a good friend of mine from college, Alex Duncan, who he's got his PhD in mathematics. He's now a professor of mathematics. And for years, he and I have shared riddles and brain teasers with one another. And he is way better at solving them. He's way faster. And I've always loved seeing his approach. So, it'll be these riddles like 10 coins or 50 envelopes or 100 prisoners. And he always does this thing where he just starts with one, right? Like we'll start with 1 coin, and usually the problem is really obvious and trivial. Then he goes to 2 coins and 3 coins, and he starts looking for a pattern. Is it only happening for the evens? Is it only with the odds? Does it only happen prime numbers? And that's what step 3 is about, right? As obvious as it might seem, and we might just want to skip ahead and focus on the harder part of the problem, doing that obvious thing and starting with 1 and iterating and generalizing, it really helps things out. And so there you're generalizing your overall, this analog or the pattern, which I'll talk a bit more about analogies. So analogies are, they are Newton's thought experiments, or they could be analogs that we use from real world experiences. And anyone who knows me knows how much I love analogies. I think they're absolutely fantastic at conveying really complex ideas. But we also need to be pretty careful when we do generalize. So there's this professor who wrote a book on problem solving, and I think he has this fantastic quote which says that analogical reasoning can create poor solutions when based on superficial similarities instead of deep causal traits. So I'll give an example of JCPenney here. So if you think about JCPenney over the last 10 years, they did something pretty different that it's not very common to see a retailer do, which they basically got rid of all their sales, and they got rid of their discounts, and they got rid of their coupons, and they went to this really simple pricing. So they got rid of this $19.99, and everything started getting like they would be round numbers like $20, which sounds really interesting and compelling, and it's pretty novel for a business to do that. But in the last 10 years, if you followed them at all, that whole process failed horribly. It just didn't do well. And that's, when you're looking at it from the outside, you get this question like, why would they do this? Why would they all of a sudden change their model so dramatically? And what were they trying to achieve? And if you know, in 2011, JCPenney brought in a new CEO, Ron Johnson. And if you don't recognize that name, then you'll know him for this, which is that prior to joining JCPenney, he was most notable for the wild success he had in building out the Apple retail stores. And all of a sudden that starts to make things click, right? Because here's this guy who did this great customer experience around the simplicity of the Apple stores where people can interact with the product, and they removed all this barrier that retail typically had. And he took that same model and tried to kind of repurpose it with JCPenney, but didn't factor in the difference between the consumers, right? JCPenney customers turned out that they really love coupons and discounts, and they hated when those were gone. So taking that same kind of approach doesn't always work. You have to be careful about that and know what are those deep causal traits. And that lets me talk a bit about patterns and parallels. So I think everyone knows, they've heard by now, that our human brain just loves patterns. It's how we survive. And when you're analyzing data or you're looking at a broader problem, that pattern recognition, it can be incredibly helpful. And a lot of that skill set comes through experience. So if you're a junior person right now, just know that it's okay, because as you experience new problems, you'll start to form those patterns and you'll encounter more and more problems, and detecting those patterns becomes easier. But Mark Twain said that if the only tool that you have is a hammer, then everything starts looking like a nail. So you have to be careful of the traps that patterns can have. And that's why step 3 is that once you form that thesis, you want to evaluate the antithesis of that thesis, the opposite. So there's this paradox in statistics called Simpson's paradox. And that is, I think, one of the best but most frustrating paradoxes, which is that once you are looking at a data set and you start to form a conclusion, like you see a trend line or you see some information there, if you just were to change something about how you've defined the data, or maybe you broaden the axis, or you change the slice of time that you're looking at, that trend that you found, it can actually completely reverse, or it can completely go away. And that's really incredibly frustrating if you're dealing with an outage and you think you've kind of figured out, oh, this is why it's happening. I can look at the graph and I'm seeing this spike, but then you just change the window of time and immediately it goes away, or it doesn't relate to the thing that you thought it relates to. So, while Simpson's paradox is specific to statistics and data and probability, I think that it actually paints a bigger picture and an important consideration for whenever you're trying to frame any kind of problem. And so talking about framing, one helpful thing to do is to work in reverse. So that's in line with that whole thinking of thinking forward when someone asks, what is the one problem we need to solve by the end of this meeting? And so I'll give these example of mazes, which I think paint a really beautiful example of this. So, if you've ever done a maze, maybe maybe you don't know that you can solve the maze faster by starting at the end and working your way back to the beginning. And some people call that cheating, but I call it problem solving. But the idea there is that, when you're working from the beginning and going to the end, you're seeing all of these traps that were explicitly designed to confuse you, and you have to go down them to find the dead end and then work your way back. But when you're working at the end, you can kind of avoid those traps because they're not in the same direction that you're moving. And so starting at the end means that you only have that one pathway to work to find to the beginning. Whereas if you're at the beginning, you have to explore all those pathways. And all that applies to mazes, but I think it really poetically captures a lot of the challenges that we have with problem solving. Now, some of the most critical and worst problems that you can ever deal with, they have what we put together called RCAs. They're root cause analyses. And they're these big write-ups. And one of the strategies when you're performing an RCA is to work backwards by asking this concept of the 5 whys. And basically, that is just asking why 5 times, working in reverse. It's pretty obvious naming. It's a little on the nose, but it's problem solving. It's not marketing. So an example there, it's a common one that gets thrown out, is you might ask, one, like, why did the Titanic sink? And the answer there that we pretty much all know is that the Titanic hit an iceberg. And then you ask again, well, why did hitting an iceberg cause the sinking? So that's because, well, hitting the iceberg, it created a hole in the hull of the ship and water started to get in. Then you ask, okay, well, why did it create a hole? And then, the answer there is because that the metal panels were easily stressed and weakened. And so then you might ask, well, why were they so easily stressed? And you start to analyze, well, it could be because the spacing between the metal rivets were actually wider than the recommendation. So then you ask again, why? Well, that's where cost savings, usually a common problem, root cause of things. Cost savings just meant fewer rivets, and so went against the recommendation, and now you have that disaster. And depending on the line of questions and answers to that, you can end up with multiple root causes. And so it's kind of just like the maze, where you end up with sort of different starting points, and it's important to consider those. And there's other techniques about root cause analysis, like fishbone diagrams and Ishikawa diagrams. But the last one that I'll quickly cover, because I think it's pretty interesting, is this great TED talk by a chess master called Maurice Ashley. And he talks about playing chess in reverse. So we have this idea about these great chess players who they can think 10 moves ahead or 15 moves ahead or 20 moves ahead. And he just says that just if you think about the sheer number of possibilities, that's pretty much impossible, and it's hard to think that quickly. It just doesn't work. But what he does is he has memorized and knows a bunch of advantageous end game positions. And then his whole game is trying to force the other player to form that board position so that he'll know he'll just win the game. And so he's not working, or he's not playing 5 moves ahead. He's playing 5 moves in reverse. So, sometimes when you're going A to Z or Z to A, it's not obvious what steps you take. And that's where this concept of stacked swags are. If you don't know what a swag is, it's a sophisticated wild ass guess. And it's one framing strategy that helps you quantify things that are not easily quantified. Like sometimes you just can't figure out what the number behind the thing is. So the idea is you want to make justified guesses about quantities for questions that you can't easily measure. So this is a Fermi problem. It's a mathematician called Fermi who came up with problems like you ask how many piano tuners are in the city of Chicago, which it's kind of tough to figure out what the number is behind that. But a more relevant example to us in tech, it might be, let's say you wanted to build a feature for your user base and you need to know, well, how large is my user base, or who's going to be impacted by it? Or if you can't generate the data behind that, maybe you have a different question, like you need to estimate your customer size in a very specific market. And sometimes, again, that data just doesn't inherently exist, or there's some complicated parameters around it and you just can't easily Google it. So how do you answer them? Well, going back to the piano example, you want to start with something that is easy to find out, which is like maybe the population of Chicago. And then you start making these educated guesses to whittle that number down. So you might ask, well, how many families are in Chicago and how many families own pianos? Like, does affluence matter in terms of owning a piano? How many schools are there that might have bands that might have pianos? Or what about hotels and rich restaurants? And so you start asking these questions and you make these logical guesses about what percentage of the number is. And so you start whittling that number down. And then you ask other questions like, how long does it take to tune a single piano? And how frequently do they need to tune, or how frequently do you need to tune a piano? Because if you're working in reverse, you might have actually started with a different way of framing the question, which is really just how many pianos does a piano tuner, this is a bit of a tongue twister, how many pianos does a piano tuner tune to make it a full-time job, right? That's their one career that they're going to do year in, or day in, day out. So, and then you work backwards from there. So the last thing, and probably the most important part about this approach, is step 3, where you want to show your work in each iterative step, because as you go on, inevitably you're going to find out more information. You're going to, realize that you made some assumptions that are either accurate or slightly inaccurate, and you have to adjust them. So you get more information and you adjust it, and that number becomes more and more precise. It's also a good way of just letting others validate the work that you've done, and then they can build from it. But importantly, I think everyone probably immediately gets the sense of, well, how can you even make that guess, right? Like you say it's 20% of the population. I mean, how do you know that for sure? And that's part of the problem, right? It's that swags are not fact. It's just a theory. It's just a guess, and it's unvalidated. And just like solutions, they don't start off as solutions, right? If you think about the scientific method, solution is a proposed solution. It's a hypothesis until you've actually proven it. And so the risk of forming any kind of hypothesis is that our bias also always gets in the way. And so it's important to prove things and avoid our bias at the same time. So, when there's multiple solutions proposed, we always have the tendency to cheer for the one that we came up with. And that's even worse when there's not multiple solutions and there is the only one solution, because everybody's cheering for that one and they're not considering alternative possibilities. There's this philosopher, William James, who has this great quote that says that, many people think that they're thinking, but really they're just reordering your biases. So the question then is, how do you know that the hypothesis that you formed is any good? So this is a concept called the messy hypothesis table. That's my term for it because it makes it a bit easier to remember. But I adapted it from this book called Cracked It. And in there, they present it as this hypothesis pyramid. But I think the messy table kind of makes it a little easier to remember. So the idea is, just think of your hypothesis as this tabletop, and each leg is a sub-hypothesis of the hypothesis. And so the table can have any number of legs, but importantly, if any one of those legs fails, then the whole table will fall down. And it's also not so obvious, but your legs, those sub-hypotheses can have sub-hypotheses, so you can keep breaking it down until it's easier to prove or disprove. But the messiness comes from, or the messy part is from MECE, which is to say that each leg has to be mutually exclusive and collectively exhaustive. Which, to simplify what that means, is basically you don't want to have redundant legs. Each leg has to be showing and looking at a different thing, and they stand independently from one another. So to give an example to kind of help make this a bit more concrete, you might say that, let's say your hypothesis is that emails are not limited by a geographic distance. From there, you might have a sub-hypothesis that says that emails will always be delivered to the recipient as long as that receiving server is available. And then you can break that down even more to say that the receiving server is available if it responds within a given time frame. So the system works well to break things down and test things, but it's not that great at actually avoiding bias. And the other thing is like, what if you can't come up with a hypothesis? So that gets you to messy question trees, which is similar concept, but instead of actually forming hypotheses, which are statements, you're asking questions. So it's a bit better at avoiding that bias. And it's a little more thorough, but it also takes more time. So sometimes you don't have the luxury of doing this, but it's the same idea, but instead of a table, think of it as a tree where you have your core question, and then you break it down into these sub-questions, each one of them being messy or mutually exclusive, collectively exhaustive. So no redundant questions. So questions, a core question might be like, what feature do you want to add to our product? And the sub-question could be, or sub-questions could be, what are the competitors doing? And then what do our customers want? Because sometimes there are different things there. And then you might have a third one that covers everything else, which is what is something that no one else has thought of. And so that way you've kind of broken it down into 3 categories. Another example using the 500-mile email is, you might ask, well, the first question is, why is that email only able to go 500 miles? And then a sub-question of that is, can you even limit the distance that an email can travel? And then you might have another sub-question like, how long does it take for data to travel 500 miles? So knowing the context around those questions becomes really important. And so when I talk about context, I'm talking about systems and systems theory, which systems theory is all about how inputs convert into outputs. And it's honestly one of my most favorite topics that I've come across in recent years. There's a great book about systems theory called Thinking in Systems that I definitely recommend people read. And it covers everything from filling your bathtub with water while the drain's open. It also covers things like how a government trying to help an underdeveloped nation by giving financial aid can do more damage than good. Or one example that I like, which is that how sheep grazing in just a common field can lead to global catastrophe. So it's a pretty deep topic, to say the least, but the 10,000-foot view is basically, there's 3 things that make up a system. There's the inputs and outputs, that's one. Then there's your connections between them, and then the function or the purpose of that overall system. So, when you think of things as a system, you start to see how things relate to one another and how things move through that system. So a good example of this is just looking at, a problem that everyone deals with at some point in time, which is, that statement of like, we just can't get new work out because we're always getting these urgent requests coming in. And so you want to ask, like, what are those factors in the system that are creating this problem? What's happening upstream and what's happening downstream? And there's a great quote that I'm going to throw out there that I really like, and says that you can only save people from drowning in a river for so long before you start to actually look upstream and see why they're falling in or who's pushing them. So that's kind of thinking about the whole thing as a system. And the critical part here is that 4th step, which is, what is the feedback loop? Because the feedback loop is what's going to create, or what's going to make or break the system. So a very easy example of a feedback loop is if you've ever sent text to someone, maybe someone that you like, and then you sit there anxiously waiting for a response, right? That's that very simple kind of feedback loop. But other times it can be like if you get a system generated alert that says that your servers are down, and then you're staring, just saying, when is someone going to respond to this? When are they going to acknowledge that alert? And you're just kind of feeling more anxious about it. So when you evaluate your problem as a system, it helps you kind of analyze everything as a whole. And I'll give a personal example of this, and there might be some people on the call who think that I'm talking about them or that they experienced this with me. I promise you, you're not actually part of that. So it's a different example, but it sounds familiar to you. So one example is that I was dealing with this mess that I had inherited, where there's a lot of infighting within the team, and then there was infighting between multiple teams, some of which didn't even report to me. And it all stemmed from a lot of miscommunication. And it basically made our system where our inputs were just complete garbage and our outputs were frustrated customers. So it was as simple as that. And I'll tell you that I as much as anyone else, love a 15-minute stand-up meeting. I love it when they're shorter, but the truth is that only really works, and it's only effective when everyone is on the same page and they're aligned and they know how things work in that system. But with the fractured process that we had, no one was aligned. And so I ended up having to broaden the audience, and I brought in different teams, some of which didn't report to me and reported in a different department entirely. So adding more people meant adding more time. We went to 30 minutes to 45 to close to an hour. And you know, what that did though is, like, by having a big audience, it was a brutal meeting and everyone was motivated to start fixing it. And we realized in that we were all part of the same system. So as we saw how the things flowed from the very beginning through to the end, we started to realize where we needed to introduce our feedback loops. And immediately as we added those feedback loops, like maybe we have a 15-minute check-in with this team at this time of day, and we only need to do that once a week. All of a sudden, those problems that we were having in terms of the quality of our outputs were getting better. And the problem was just naturally getting solved that way. And we went from 4 different teams to 1 team, because we were all aligned and everyone knew how the work that they touched worked its way through that system. So just remember that, you know, garbage in, garbage out is not quite accurate, because garbage actually ends up compounding a system. It makes more garbage rather than just the same garbage. So fixing one bug that has poor requirements, I should say, doesn't mean that you now have that bug fixed. It's that you have that bug and more bugs with it. And so you're actually exponentially increasing the work that needs to happen. So to wrap that up, just look at problems as a system and expand sometimes what you're seeing as that system. Look upstream and downstream. And then this is the last one that I'll cover, which is reframing, which I think is probably the most creative and design thinking related strategy. So if you're not extremely technical, if you have like a strong creative artistic streak, this is one that I think you'll really appreciate and enjoy. Which is, you know, if you're thinking about problem solving as a system, as in systems theory, like I talked about, then reframing just really evaluates the whole thing. So the idea is centered around first framing the problem, and then you reframe it. So with reframing, you look outside that original frame that you formed, and then you rethink what your goal is, and then you examine the bright spots. And that's important, because sometimes you need to ask that, where is this problem not actually a problem? Where is it working? Because in that, you might find the things that actually contribute to how it worked or how it doesn't work. The last 2 are important because it helps eliminate certain bias or certain things that can contribute to problems, like looking in the mirror. So how am I contributing to this problem? Is something that I'm doing, it might not even necessarily be a personal relationship. It could sometimes be technical. Is my approach actually impacting this or making this problem worse? And then taking the perspective of either stakeholders or people who are involved in the problem, and kind of understanding what is their goal or what do they need. So there's this really, really great book called What's Your Problem? And it's all about reframing. Another book I definitely recommend reading. And it gives this example that I absolutely love, which says, you know, let's imagine you're the property manager of a building, and that building only has 1 elevator. So the tenants of that building, they're now threatening, and they're saying, you know, we're going to move out because we are sick and tired of this elevator. It's just way too slow. And so now you have to figure out, like, what do you do next? Because you're about to have a bunch of people break their lease because of this slow elevator. And so if you did everything that I've covered so far, you're really focused on that elevator. Like, why is it slow? Can we speed it up? And remember back to that 500-mile email when I said that sometimes the problems that we're dealing with are not the problems that we need to solve. So reframing helps you understand that the elevator is actually not the problem here. It's much simpler in a lot of ways, and it's just that people really hate waiting. And that might sound like an oversimplification, but there's actually a study that UX experts have done while studying progress bar animations, which I know sounds super exciting, but what they showed was that when you just have a regular progress bar that's moving forward, it feels slow, people don't like it. But when you add a gradient to that progress bar that's moving in the opposite direction, it makes time feel fast. And so that wait feels less boring, I guess. It just feels faster. And Jose's way ahead of me. So, yeah. So think back to what I was saying about like that toaster and problem avoidance, right? If you ignore that toaster and find a different way of making toast, then that toaster still remains broken. And with a slow elevator or progress bars, this is more nuanced because it's not that you're avoiding the problem, you're actually finding the root of that problem, which is that speed is largely subjective, and regardless of how fast the elevator is, waiting is always going to be a pain. And everyone hates progress bars, right? So even when things are fast, people will still complain. And so you figure out, how do I resolve the experience and not the speed? So with the elevator problem, yeah, it's about, installing some mirrors, or maybe you add the television, something just to distract while they're waiting for it. Time seems to go by quicker. With progress bars, you can probably even sometimes, and now it's like more common to do this, where you just perform the task in the background and you give an update when it's done. And so that way you're not blocking the user. But the important thing is to also always fight that urge to immediately go into that solution mode. And you want to just take a beat and ask yourself, like, is there a different way that we can be solving this problem? And what I mean by that is that, I'm a coder. I've been a coder for tons and tons of years. And I am a coder because I always loved writing code before I even entered college. But I'll be the first to say that code is not always the answer. If you have a broken process, if something's just not working right as far as the business process upstream, then you want to introduce code to help work around that problem. You're still going to have a broken process, but now you've also introduced code that will need to be maintained. So your problem just got more expensive. It didn't get solved. So reframing, it often gets glossed over as this idea of, are you solving the right problem? But I think that just does this whole technique an injustice, because reframing is where you actually see the real problem, and that's where real innovation and real problem solving happens. You're no longer focused on fixing the symptoms, for one, but you're also not even fixing that root cause. You're actually instead questioning your own bias, those of others, and you're going against the status quo, and you're swimming against the current. And there's this logical fallacy called the appeal to tradition, or the appeal to common practice, and that's when everyone's heard it, where they say, well, we've always done it this way, or that's just how it is, and we can't change that. And that's where that fallacy creates a bunch of resistance with reframing, because reframing can be pretty bold and audacious and ambitious, but I also don't want to over romanticize it either, because it does mean a lot more work, and you do have to balance that against the time that you have. But when you can do it, and when you can reframe the problem in the right kind of way, it does also lead to the most disruptive innovations and solutions. So remember with that toaster, I mentioned that we prefer solutions of a certain kind, the ones that avoid friction and tough conversations, and reframing just actually faces the problem head on. All right, so I covered a lot, but I'm just going to quickly recap what I've gone through. So there's the low-hanging fruit. There's simplifying by adding, subtracting, isolating, and changing the scope. There's analogical and pattern analysis. There's retrograde analysis, which is that working backwards. There's causal analysis, which that's that asking why 5 times. Numerical analysis, that's those stacked swags. The hypothesis pyramids and issue trees and systems theory, and then reframing. So real quick, what I'll cover is that 500-mile email now. I'll say that I want to make my college professors happy, just by quickly quoting Ernest Rutherford, who said that all science is either physics or it's stamp collecting. So if you took high school physics, you'll know that distance is equal to velocity times time. So we had the distance, 500 miles, and velocity is fixed at the speed of light. roughly. There's a little bit of resistance on the wire, but we can just say speed of light. So really the only variable in this problem is time. And so I'm going to gloss over a ton of like technical stuff, but the simple part is that on that server, there was one configuration mistake, which had the timeout at 0 seconds. So it wasn't truly 0 seconds because it takes time for a computer to evaluate that 0 seconds have elapsed. So it actually took about 3 milliseconds. So 3 milliseconds, and in that time, an email traveling at the speed of light will go about 500 miles before the server times out and says that it's going to cut off the connection. So that's an incredibly difficult and annoying one, but it's a great read. And I definitely recommend you can just Google 500-mile email, and the way that guy dissects it is great. So I'll just quickly cover some of the biases and pitfalls we have to avoid. Confirmation bias is really where you want to be worried, because that's where your theory, you're the champion for it. So new evidence is you're only gonna use it as a way to confirm your existing theory. So you need to be careful doing that. There's cognitive dissonance. That's where new things arise and you want to quickly explain it away. Like maybe your immediate reaction is that professor is old and he probably shouldn't be emailing. Like emails aren't limited by 500 miles or, is limited by distance. And then there's lastly, like my favorite, which is pretty popular right now. People talk about it a lot, which is the Dunning-Kruger effect, which basically says that those with less skill have this tendency to overestimate their skill at something. And so they're kind of concerningly overconfident about how little they know. So, an example of that is just imagine you're sitting in your car one day and you're waiting for your daughter's piano lesson to finish up, and you start to think to yourself, I should do a talk on problem solving. I'm going to end here. So I'll say that I love problem solving, and like everyone, I hate creating them. But the key to remember is that mistakes are only mistakes as long as they happen once. So I will share that I have deleted entire customer portals, and I have deleted our corporate website, and I've survived. I've actually also uploaded 250 images to a customer's database, and it had nothing to do with what that customer was about, but they all of a sudden have these images. And I accidentally, and I want to stress accidentally, made 250,000 users' profile pictures a picture of myself. Again, I'm stressing that was accidental. But, other than the low-hanging fruit, if there's one other thing that I want folks to take away from this, it's that problems occur. And after a problem does occur, what are the systems and the processes and the actions that you're putting in place to keep it from happening again? So I've been talking a lot about problem solving, but what I think I'm actually really good at is writing great root cause analyses documents. Those are your best friends. And when you learn to write them, when you put them together, make sure that they're detailed and clear. You don't want to cover things up. You don't want to editorialize, because the truth is that they become great opportunities for learning. And when you're in the middle of it, it's a great resource to pull up and see what happened last time. So that's pretty much it. Those are the books that I used, and I love them. I think they're great reads, and I definitely recommend reading them. So I don't know how much time I went over, but hopefully not by too much.
Oh no, I'm actually glad you went over. It was awesome. So thank you. There's so much packed into this. I'm glad that we recorded it so we can all unpack it again. Are there any questions?
I thought it was a really interesting analogy, because it seems to be this cool intersection between like actual physics, like our actual understanding of the world, and imagination. Because like when you were describing that illustration, you're getting the student to visualize something, right? So there's like this amount of imagination, and then the natural conclusion of that, you're making them extend it. But also once there's a turning point there too, where once they go off the board, you reframe it, right? You zoom out so that you're on the planet, and at that point it's like, okay, I wonder if there's a cognitive shift where they have to, if they're still extending their like that line, or if at that point something that they've learned from when they were a kid or something starts to kick in and say, oh well, I also know that this isn't going to fly off into outer space, it's going to continue going around the earth because of gravity. Like that's a fascinating question. I thought it was cool.
I mean, I would show my arms, but I got chills from what you just covered. Because I mean, you're exactly right. Like I think that's actually, you've dissected it even further, because I think that is where the shift happens, because you do all of a sudden take into account the curvature, right? That's where you all of a sudden get, like, it hits you in the face that this is what's actually going on. And I will say that if you were to extend that exercise, which is basically like what space travel is, right? The further force you put into something, that's when you start actually having rockets leave Earth, right? So
Right.
it does extend onto that. So you're exactly right.
That's great. I think.
Alicia, I've got.
Okay.
Oh, sorry.
No, go ahead. Go ahead, Ryan.
Yeah, thank you, Elisa. Great. This was a lot of content, a lot of stuff to chew on. Appreciate it. I'm curious your take on how to handle this in meetings, because in meetings generally, I mean, depending on the type of meeting, obviously, you're in with people from business, you're in fellow developers, you're in with maybe networking systems, maybe HR, whatever, just a lot of different people. And so there's a problem you got to solve. And my experience has been, you walk in, it's like, well, what's the solution? It's like, well, hold on, what's the problem? I mean, how do you, like, are we all clear on what the problem is?
Yeah.
How do you handle, I mean, obviously you don't say, hold on, let me give a talk, just 1 minute, let me give my, so how do you,
let me get my slideshow out.
Yeah.
Well, it's funny because that whole thing reminds me of, like, I don't know if you've ever seen the movie Big with Tom Hanks, but it's like, he's got the building and he's like, it turns into the robot. And he's like, kids don't want to play with a building. Like he puts the whole thing into question, right? And I thought about using that as one of my slides on reframing. But you're exactly right. I think that meetings are a great example of where everything is done poorly unless someone already is steering it in the right direction. And I try, when I do get those very ambiguous kind of meetings, the first thing that I do before the meeting starts is I do try to ask, what is the purpose of this meeting? Like, do we need an agenda, right? Sometimes that feels a little like just making work for people. But when you ask that question of, like, what is the agenda? Like, what are the topics we need to cover? It starts to make people ask the right questions about what we're trying to achieve. There's a great book, I think it's Peopleware. And if it's not that book, read it anyway, because it's a great book. But they talk about how meetings have become these kind of like messy, just sort of like ambiguous things that we're going to go in, we're going to talk for an hour, and then at the end of the hour, we're done. And things don't work out that way, right? So they come up with, like, the whole aspect of working meetings where we're going to work on this problem and it's going to take as long as it takes. It might be 45 minutes, it might be 3 hours, but we're all focused on this problem. And the goal, the trigger that ends that meeting is solving that thing. And so thinking in that way, you almost, if you're in the meeting already, it's almost too late for that. But I think that's where I've seen it time and time again. And every single time I'm like, I should have been the one that said that, is when people ask that, what are we trying to solve? Can we distill this down? And some people are so good at very, without sounding like jerks, but being very authoritative, they'll say, or assertive, they'll say, like, what are we trying to solve? Let's simplify it. No, that's too complicated. Let's bring it back down, and they'll just keep pushing on that until they distill it down to something. And I think sometimes, unfortunately, you need to have the right kind of title to be able to do that, because the lower you are on that ladder, the more you just seem disruptive.
Yeah, I'm very low, so I don't want to stick my neck out.
But honestly, though, if you feel that way, walk out of that meeting and talk to your manager about it and say, hey, listen, can we break down how that meeting worked? What were your impressions of it? Because I feel like it wasn't solved, or I don't feel like we addressed the right things in there.
Yeah. Thank you.
Yeah.
I wanted to add something, because this whole session, first of all, was awesome, and I did something very similar for like an all-day session where we were given kind of teams at tables to work on different problems together. And one that stood out to me was one individual was voted as the communicator, and the communicator had to leave the room, look at this thing outside the room, come back, describe it to the group. They'd ask a question, he'd go back out and then kind of go back and forth, and hopefully do it within the time that was allotted.
Yeah.
And after the whole session went by, the learning point was, no one said you couldn't move the table outside and speak closer to the information was there.
Yeah.
And so for me, it really highlighted and kind of changed my way of thinking about things was, you know, we have our preconceived notion about what the rules are and how things can be done. But every now and then it's okay to kind of go, well, no one ever said I couldn't do this.
Yeah.
Let's break out of what we think the rules are and do it.
To extend that, that's one of the most frustrating things, one of the best and most frustrating things, like in a classroom management, from a classroom management standpoint, sometimes when you're teaching, is often your most creative and most like your best problem solving students will be the ones to give you the most problems when you're trying to structure a class or something. And they say, well, why can't we do something this way? Why can't we do it this way? And it's like, oh, that, okay, yeah, you can do it that way. Or it's like, well, no, your task is this instead.
Yeah.
But yeah, oftentimes it is. That's, I think, when people talk about killing creativity, that's where it happens if you don't channel that in an appropriate manner.
Yeah, well, so two thoughts on that, because I think that's a fantastic one. Is more fun, but the first one I'll say is that, you know, I'm not someone who generally, like, if I talk about my role, talking about my title, and here's my list of responsibilities, I don't think in that way. I'm not a swim lanes person. I'm gonna, like, if someone's not doing something or something, if they need help or whatever way I can, and it's not my domain, I will go do that. It's just my natural instinct. I'm not saying that to put myself on a pedestal, because it also is pretty disruptive in different circumstances where you sometimes need to focus in certain areas. But what I will say though is that it does have me need to sometimes be in the meeting and say, if I'm distilling things down to a problem, I have to be in my own zone and say, okay, if I'm distilling the problem, here's what I need to know, right? I have a team of engineers that report to me. What I need to know is, do I have enough for what is being asked of me? Or do I have the right skill set on the team, right? I might be thinking all about the product and what does it mean in terms of a roadmap and will our customers be happy about it? But if I start talking in that way, I'm ignoring my more core problem, which is I need to know who I need to hire, right? Now that I'll still have those questions lingering. So if I'm not seeing anyone else ask them, I might then ask them. But that's the thing, is like you want to bring it down to what is my most basic concern here. But interestingly, so if there's a show that I absolutely love, it's a British show called Taskmaster, and that show is built on that whole premise of, it's a bunch of comedians, so it's pretty funny, but they take it seriously. They're pretty competitive, and they go to some location and they get this task. And sometimes the task is really like, you have to do this thing. But all of them are thinking, how do I do this thing? Not in the way that everyone's expecting me to, but in the way that solves it and gets the best thing. So like, I'll give you one example. I apologize for the spoiler, but it'll help you kind of immediately capture it, which is the thing says there's like a little pea, like the vegetable. Hopefully it's not a legume and someone calls me out on it, but I'm going to call it a vegetable. And it just says, propel this pea the furthest. And it has to land on this red rug carpeting thing. And so, you know, first guy just takes it and he throws it because he thinks that's what the task is. And then this one guy gets fixated on the word propel. And he's like, propel, that doesn't say throw. So it just means I have to make it move. And so he grabs this wheelbarrow and he puts the pea inside and he rolls it around and he does like 3-4 laps, and then he dumps it onto the red carpet. And you think, oh, this is a guy who's going to win, until one guy comes along and he takes the pea, puts it on the rug, rolls it up, picks up the rug, and he goes and hails a cab. And he like looks in his pocket. He's like, I've got $200, drive as far and as fast as you can. And he's the one who wins, right? So it's like, it's very much that reframing kind of thing that I absolutely love about the show. And I definitely recommend watching it. I will say it's got some rude language in it, but you know, I don't know if there's censored versions or not. So.
You know, I was gonna ask, okay, where do I read more to get all this? And then you put the great reads up, and I was like, oh, perfect, there we go.
Mm-hmm.
But yeah, each one of those subtopics it like seems like this is just a really, you know, high level look. It's fantastic.
Yeah, none of these are. Oh, I'll say the last one. How would you move Mount Fuji? That is explicitly the book written on about Microsoft interviewing styles, where they'll ask like really bizarre questions, and it teaches you how to break down those kinds of questions, but they're much more geared to weird questions as opposed to the broader problem solving. Thinking in systems is not necessarily about problem solving, but it is once I read that, it really kind of gave me a different perspective. Again, it was a thing I was doing naturally, but it framed it for me so I could actually do it in a certain order and think about it in terms of what am I missing. And sometimes the most obvious thing is the feedback loop, and you forget, oh, if this person just spoke to that person, or if we just had a way of getting this back over here so we can validate it, it just simplifies it. But the two in the middle are strictly about problem solving in broader senses. But there's another book that I'll mention. I can't remember the name of it. Oh man. But there's another book out there that's really good. I'll say that. I'll try to remember it, and then
That's a cliffhanger right there.
yeah, I know. It's terrible. Maybe that'll be my next talk.
I know, right?
Let's see if I can figure it out while we wrap up, and I'll quickly say
Okay.
it.
This
Well,
sounds
thank
like
you.
a problem.
Yeah,
An
exactly.
Elegant Puzzle. That's what it's called. An Elegant Puzzle by Will Larson. So he's a technologist, and he rose through the ranks. So he started as a developer, became a lead manager, manager of managers, and director, and that kind of thing. And his book is phenomenal because it talks about all kinds of ways in which different problems come up. He's a big believer in systems theory too, so he'll kind of reference thinking in systems. But yeah, that's a really solid book.
What is the title again?
It's called An Elegant Puzzle, and the author is Will Larson. Here, why don't I type it to make it easy?
Well, thank you all for being with us today. It's great to be around passionate people about what they do. Thank you, Alicia, so much for hosting, and you can be on our platform anytime and host any kind of tech coach. So a little clap for Alicia. Thank you so much.